So we also get a dual map for any map that we have between vector spaces. So for an element of LVW, the dual map of T is denoted T prime, and it's an element of the space of linear maps from W prime to V prime. So note that the order got reversed there. And it's given by just composition. So T prime of phi is defined to be phi of T for, any element of W prime. And so I will refer to this as precomposition from time to time, just to indicate that T is being applied to an element before the functional. All right, and so it's frequently handy to doodle out a little picture of what's going on here. So we've got, here's V, and it's getting mapped to some other vector space W by T. And that means that W prime is going mapped to V prime by T prime. So we just prime the heck out of everything, right? And what we have is that some element phi here of the dual space. So phi is something that sends, it's a function from W to F, and it's getting transformed into some T prime phi, which is sending V prime, I forgot a prime, sending V prime to F. All right, so what does that look like back in the original picture? Well, if we visualize the base field being down here, the scalar field, then phi is going to be some function that goes like this. And then when we look at the composition, what we're actually doing is we're composing along these two right here, yeah? So we're doing T first and then phi. And so that gives us a map from V to, actually, you know what? I like green. Let's stick with green. Oh, except I don't like green when it's bendy. There we go. That's slightly better. So this guy right here, this is going to be our phi of T. And that is how we define T prime, right? So that means that in this picture, T prime is actually an arrow between arrows. So I will denote it with a double arrow like that. So it's mapping the vertical T, this vertical phi arrow to this diagonal T prime of phi arrow coming down like that. So that's a picture of what T prime is doing. Okay, so now we have a proposition about this. And this is 3.101. I'm getting up there. 3 is a hefty chapter, right? Okay, so for if we have two linear transformations from V to W, then this is going to tell us how priming works. So first off, if we have S plus T and we prime it, we get S prime plus T prime. And secondly, if we have a scalar multiple, then we get lambda times the prime of it. And I'm sure you saw that coming a mile away. And then we also have that if T is in LUV and S is in LVW, so that their domain and range match up, then we have a third property of these maps, and that is that the prime of a product or composition is T prime S prime. So in the backwards order. Okay, so let's see what's going on here. I'm not going to prove this one. The proofs are all just definition chasing and very straightforward. But let's see. So if we go from U to V to W, and here we've got T doing the first one and then S doing the next one. Then let's see what's going on. So from W, we've got a map coming down to the scalar field. And so if we start with a phi over here, then let's see. So then we're going to have the composition over here. So this is phi of S, right? So if we compose, then we're going to be starting with something that's in V and ending with something in F. And that's how we define S prime of phi. And so there's our picture of what S prime is doing. And then we can play the same game again and pull it back all the way to something going from U to F by precomposing also with T. And so now here we've got phi of S of T on the end here. And so then what the theorem is looking at is it's saying, well, what happens if we look at the composition across the top right here? So the composition across the top, this is ST, right? And so what the theorem is telling us is that if we look at ST prime, which is going to be pulling back across the composition right here, so this is ST prime, then what we get to is the same thing. So ST prime applied to phi is, and then this theorem is asserting this red equals sign right here. That's what's meant by number 3 in this one right here. Well, actually, yeah, let me see. The fact that doing the blue double arrow followed by the green double arrow is the same as the yellow double arrow. Sorry, that's what the content of number 3 is here. I will amend that. There we go. So here, the red equals is between these. I'll make this black equals so it doesn't look as important. All right. Okay, and so parts 1 and 2 of this proposition can be expressed loosely by saying that prime is a map from LVW to LW prime V prime, and as a map from LVW to LW prime V prime, it is a linear map and it is contravariant. And so by contravariant, I mean that it turns arrows around. And I'll refer to this from time to time as the old switcheroo. When you dualize things, they go inside out and backwards. And so in particular, arrows go the opposite direction. If you have an inclusion between V and W, then you expect the reverse inclusion between W prime and V prime, and things of that sort. And let me also just point out real quickly that this notion of linear here is talking about priming, sticking primes on everything. And then if we go back to the T prime that we looked at in the first proposition right here, when I talked about this guy being, let's see, when I talked about this guy here being linear, that's talking about the map T prime after you've put the prime on it this thing is linear. So there's a slight distinction between linearity of primes there.